So thanks everyone for coming. We are going to talk about binary sizes in the next, how long will that be? 60 plus 90 minutes. That's 2.5 hours. That's a lot of time. So if you have any questions or remarks, because probably you know certain parts better, you have some ideas what to do, feel free to interrupt at any time. This can be quite interactive if you wish so. But let me introduce myself. Again, I have problem with this. Well, fine, I'll use the space. So let me introduce myself. My name is Sandor Dargo. I work as a senior engineer in Spotify. So it's not the embedded word, but we have some embedded though, but I'm not there. And well, I enjoy writing. Maybe I enjoy writing more than talking. I write not only but mostly about C++ and some books that I read sometimes about Stoic philosophy. I love traveling, and I love everything that is food related. Just for you to understand, I like, for example, sourdough baking, and I passed just this last year a couple of wine tasting exams in France, where I live. So it's not that I moved to France for that. And I have two wonderful, very active kids. And big thanks to my wife that she's taking care of them so that I can be here with you. But that's enough about myself. Next question. Why do we care about binary size in 2024 when, well, storage is cheaper and cheaper and more abundant? Why? Well, there are three reasons, I'd say. One, there are devices with limited storage, and those who work here in the embedded world, well, that's why you care about binary size mostly. That's not the reason why we care about binary size in Spotify, because there are devices with limited bandwidth. So here, for most people, well, most of us have some kind of an unlimited data plan. Well, I think I have 80 gigabytes. I consider it unlimited. I never use even half of it. But other people in other countries might have different limitations in terms of bandwidth. And we learned that, I think I'm not supposed to say exact numbers, but like each megabyte you can shave off from the app, from the download, from the installable APK. Well, it considerably changes how many people will actually install and use the app. So that's why binary size matters for us. And there is another part. I'm not aware of the details there, but I know that some researchers in our company found that, well, actually, it has an environmental impact how big the binary is, because the smaller it is, the less the emissions, CO2 emissions will be. So maybe that's also something that is worth considering. And there are some personal motivations on my side why I wanted to learn more about binary sizes, why I prepared this talk, and why I wrote a lot of articles, and I published a small ebook. So whatever I'm saying here and even more details are available in this ebook. Don't worry, I'm not trying to sell you stuff here. I will post in the Discord channel a link from where you can download it for free. You already paid to be here. No reason to pay more. So I wanted to understand the C++ binaries better. I wanted to recognize a couple of patterns that are leading to binary bloats. And I wanted to understand the effects of modern practices on binary size. So these are my personal motivations to learn more about binaries. So let's move to the agenda. We are going to learn a bit about binary files. This will be, I think, the most boring part of the 150 minutes, but probably it's worth knowing a little bit more about binary files if we want to optimize for binary sizes, though it's not 100% necessary. Then we're going to see coding practices which affect binary size one way or the other. I think for most developers, That's the most interesting part. That's where we like to spend our time in Spotify, in the team where we worked on binary sizes, but it's not the most impactful. I remember that it said, oh, okay, we worked on this nice PR and we removed 80 kilobytes from the library. And the library is somewhere between 20 and 100 megabytes, depending on the compiler and whether it's release or debug. Well, it made us really happy. But when we changed a few compiler and linker settings, well, you know, just you add one flag and it can renew megabytes. So that's probably more impactful, but less interesting. And then we will see the intersection of coding practices and compiler flags. Do you have any guess what those can be? What I mean by the intersection of compiler flags and coding practices? Yes? Exactly. You found the two, RTTI and exceptions. Exactly. Those can make a big change. So let's talk about binary files. And I tried this one again. Well, no, it doesn't want to work. So let's start here with a mini agenda of what we are going to speak about. First, how binaries are generated. Then the main parts of an executable. Then some of the main characteristics, which, well, usually, you know, nowadays binary formats, they have all the positive characteristics, but it was not the case before. We're going to see more in detail some different formats and also how to inspect binary files, how to look into them. Well, oh, okay, we'll get back to that later. So, yeah, I was afraid that maybe it's not so easy to read that, but I promise you, this is the only slide that will be like that. So, in the beginning, you have source code. Let's say you have a CPP file, main CPP. So first step, you will pass it to the preprocessor. It will do whatever is necessary. For example, okay, it will include the header files. It's you know, just a textual replace. It will resolve all the macros. Then you have a temporary file. Then the temporary file will go to the compiler. And out of the compiler, you will get the assembler file. I think yesterday at the Lightning talk, someone mentioned that if you compile with dash uppercase S option, you will get that assembler file. You can have a look at it. That's actually quite interesting if you want to inspect binary files and you want to understand what happens. But in order to to shave off a couple of kilobytes, megabytes, you don't necessarily need to do that. But if you are interested more in details, it's probably useful to do. Then it goes to the assembler and you will get some object code. And it goes to the linker, takes library files, and at the end, you get an executable with a considerable size, or you get maybe a shared library, depends here. I went for the executable. So, what are the parts of an executable? Again, the header. Try it again, one more time. Okay, no. That's it. You get text section. Usually you will have the code in it, and it's read-only. You will have different data sections depending on whether you have initialized or uninitialized data in it. You have the read-only data section. You have symbol table, which can be quite big. You can limit that. You have the relocation information depending. Okay, it will contain details about how to move certain parts of the executable when it's loaded into memory. How to modify the addresses, and again, some import procedure linkage tables, which is important again when you load things, and the export table to list what is available outside as well. And exception handling information that we can remove later on, that we can actually kind of remove if we disallow exceptions if we can do that, it's not always possible or desirable. And the debugging information, which will obviously will be part of the debug builds, not the release ones. So what can be some main characteristics? Does the format support only one platform or several ones? How it handles symbol resolution, linking resolution? Does it support position-independent code? Again, nowadays, these are supported. Back in time, it was not the case. Even NDNS is a characteristic, so whether you at the lowest address you have the most significant bytes or the least significant bytes, what's the architecture, extensibility of a format that used to be different, what they designed binaries for, but things are changing. Now, what are the most important formats? So let's have a look at a couple. You have the A out. It's important to know what it is, I think. Then we had cost. We have nowadays ELF, PE, MECO. We'll get into a bit of details about those. I will just kind of skip some slides, but you can look at them later on if you need those details. So A out. Who has seen A out? When do you see it?
You didn't specify your output.
Yeah. And we even call it A out nowadays. On the other hand, it's not really A out that is the output, but for historical reason, we still call it like that. It's called the assembler output, and it's a heritage of the 70s. I say heritage because we still use it in many simple examples that, okay, we compile to A out. It was a format, which is, well, still in use, still can be used somewhere, but not really widely used anymore. It's very simple. It has a header, a text segment, and data segment, and a symbol table. And I would say mostly that's it. It doesn't support shared libraries, for example, or position-independent code. Yeah, but it was the first, well, maybe not the first, but the first well-known, widely used binary format for C++. Then we had the Common Object File Format, abbreviated as COFF. It was the replacement for A out. First, it was used on Unix. Then later, they used it for Windows as well. Now, this started to support larger programs and also contain debug informations. But it has been replaced as well by some other formats. And we'll see that well, this we can consider really cross-platform, but many that are used nowadays are less so, or it depends on what you consider cross-platform. So let's start with ELF. That's an executable and linkable format. It's used on Unix-like systems. If you consider that cross-platform, it's not only on one, it's on several ones. It supports, well, what we are going to talk about now, ELF, P, MECO, these are all support shared libraries, position-independent code. But as you've seen, it was not the case before. That's why I find it important to mention. You can, it supports debug information, and all of them like to emphasize in their documentation that they are designed for performance and extensibility. Well, good. Again, you have the header, which is quite small depending on what kind of system you use, 32 or 64 bits. It can be like 50, 64 bytes. It has the E indent. It will be better, but this is a bit boring, I know. It stores file type, the encoding, the versions, whether it's an executable, shared object, or object file. It stores some addresses for program execution start and offsets for the different program and section headers. That's something you have to store in the headers. But what are the common sections? Well, you have .text for the executable code. You have the data for initialized data, BSS for the uninitialized, RO data, read-only data. You have the sim tab for symbol table, str tab for string table. That's pretty much what you have in ALF. We could go more deeper, but it wouldn't really help. You have the Mac object that is for Mac OS and iOS, and well, anything that is Apple related. Their sections are grouped into segments. And again, this supports everything that a modern binary format needs: shared libraries, position-independent code, and debug information, as we saw. And they also say that they are designed for performance and extensibility, like all these. Well, the header contains details as well here, like the architecture, file type, some sizes and locations of the load commands. And they play a central role. Load commands in Macro. You have the different ones for segments, for symbols, dynamic symbol table, and many more. Okay. You have the text segment. It groups some sections. You have well, it's read only. Again, it contains executable code and constant data. It is usually the biggest segment of Macro executable, and it can be shared between different processes. So it's good that if you have multiple processes, okay, this doesn't have to be loaded several times. And yeah, it contains several sections, like the text section for the machine code, stop helper for referring to external functions, and you have the const section with all the constant data in it, and even C string with the null terminated, still C star strings there. A bit more. You have the data segment. It's read-write area. So what it means in practice that it must be copied by each process, unlike the previous text one. And there are many sections, and I'm not going to list all of them. The most common ones are data, which contains initialized variables with static storage duration, the BSS with uninitialized ones. You have const uninitialized extern globals here as well, and constant data needing to be relocated in the common section. That's pretty much what you have in the data segment. Then we have portable executable format, which is used mainly on Windows, different Windows systems, said to be designed to be compact and efficient, and it supports everything that the previous ones, shared libraries, position-independent code. Nowadays, these are musts, like debug information. If we, it's interesting that, okay, don't copy-paste text. So in the PE header, you have again the signature about machines, their target architecture, and you have a lot of data, like when it was generated, the number of different sections, and different details that I left here so that if you are interested later, you can look it up. I go over this. It has an optional header with a lot of different details that you won't need in most cases. We said that the Macro had segments. They group sections into segments. In the PE for Windows, there are no segments. You only have sections which are specified in the section header. You have the resource section, relocation section, some debug info, and all the necessary, all the others that you normally have. You know, the text, the data, the BSS. That's kind of common. And with that, we successfully finished this one. You see that you have different formats tailored for the different platforms, different operating systems, Unix likes, the Apple ones and Windows. The key characteristics and design goals nowadays are quite similar, but the implementations are different. Then the question is, and we are getting into more practical parts, how to inspect binary files. Do you inspect binary files? Do you want to look into those? What do you use? Mm-hmm. That is something you can use, yeah. What else? Mm-hmm. Yeah. Yeah. I listed those and a couple more. You have size, just to get a quick overview on Linux-like operating systems. It gives info about the different sections. So you will get basically the size. It's something very, very basic. But, well, you know, if you just want to look into some small program, want to understand better what goes where, maybe it's worth looking into it. Then you have objdump, as you said, to see the section size and a little bit more. It's part of the GNU Binutils suite. You will get the file format, different sections and sizes. You see that this is a bit more detailed. The output is a bit nicer. You have the sections, the sizes, even the addresses, and you see whether it's more like something that is in the text segment or in the data segment. It's not bad. You have nm, just another utility from the same suite. It will list you symbols. You will see what's available, and well, if you look up the documentation, you will see what all those different letters in the beginning means. It can be helpful to look into some binaries. And my favorite is Google's McBloaty. It's open source. It's a CLI tool developed by Google. We are free to use it. And it will give you more detailed insights of the binary. But that's not the best thing in it, I think. The best thing is that you can bundle up different files. So for example, I don't know, you have an executable, you have a couple of shared libraries, you can pass them all in, and it will group the sections up, and you see them overall. You don't have to do the math for yourself. So you see it's very easy to combine different files. Not in this example, but basically you just have to pass in several files and it will do all the math for you. And you will get the file sizes. You will see relatively how big it is compared to the whole file. It's very practical, I think, especially when you don't want to inspect just one file but several ones. So you can download it from GitHub and then install it for yourself. Really cool stuff. Now we are going to go into, I think, the most interesting part, the most enjoyable part, ways of coding to reduce binary size. But before we go there, do you have any questions or remarks? No? Okay. So what are we going to talk about here? We are going to talk about object initialization, member ordering, special member functions, virtual functions, templates, related node passing functions around, and a little bit about constexp functions. So these are the topics that we are going to cover here. It's important to note that not everything is a best practice that shaves off a few bytes. Some are. Okay, there are some stuff that, okay, we'll show that, don't know, let's take this example. So for example, I even read it in a book. It was really not well phrased, to say the least. Well, you know, you should declare your destructor virtual. In any case, I was like, no, you shouldn't do that. And you shouldn't do that because of several reasons. One is binary sizes, because it will really bloat your binary if you introduce virtual functions virtual destructors. You shouldn't do that if you don't need them. And actually, it's just the best practice in any case. But we will see other practices in order to reduce the binary size, which are otherwise, they are not really best practices, and you shouldn't do them. So some things are simply trade-offs in order to optimize for binary size. But it's the same with everything. If you come to a conference, usually you will get to see a lightning talk where they explain, and don't get me wrong, they are one of the best lightning talks. Okay, that's how we print usually. I'll print 100 times faster, and it just takes me 100 lines of really obscure code to print this number. And well, they are nice runtime optimizations, but it's not the best practice. You shouldn't do those things. It's the same with binary sizes. So first, we'll talk about object initialization and binary size. So let's start with something small, short code, yet it will be quite big. If you compile this, what do you expect as binary size, more or less? You can compile with O3 or OS. Yeah, for almost nothing, right? For almost nothing, you will get almost 100 kilobyte, this little piece of code. Okay, so there are several reasons of that. Well, here, okay, we can check the exact size. You see it's almost 100K, but why is it so? Well, most of the binary is in the data section, and that's why you calculate it there. It's like, okay, it should be at least 80K because you have 10,000 objects there, and each one contained 2 integers, if I remember well. So it should be about 8 kilobytes. So yeah, and that's what you get. Well, that's what we asked for. That's what we get. Bloaty tells us it's a bit big. But why is this so huge? Well, relatively huge. Well, it's because of 3 things: the container, the storage duration, the initial values. And actually, we need all of these to have this binary so big. I'm not saying that you should do this, but maybe heap allocations would shrink your binary. Well, they would, because dynamic allocations might keep your binary size smaller, because then it cannot be done at compile time. Well, yeah, not getting into the constexpring vector here that we discussed yesterday. Well, it will obviously slow down your runtime. So for example, if we change the previous example to use std list or std vector, which will do heap allocation, then we'll see the binary size shrinking. Well, everything that is a C-style container or std array, they might be large. They won't be necessarily large, but they might be large. Whereas with a std list or vector, you just cannot have this. And you see the sizes here. If after some iterations, you will see that, okay, with the array, with the C-style array, well, array is just a fancy C-style array, but much safer, is the same binary size. Whereas if you use vector, it will go down to 33, 40K. That's much smaller. You see that even though the runtime is much higher, it's much slower with the vector, because you have to initialize then at runtime. Should you replace the array for vector if you need an array? No, that's not what I'm saying. but it's probably worth knowing what contributes to big sizes. And well, when you try to optimize, you don't always do things that are very meaningful otherwise. I'll share some examples later. So yeah, again, you see that for std array we had like a 50K text section, and in the data section it was almost 80 kilobytes. When we use a vector, you see it from the name of the file, then the data section is much smaller. It's only 15K compared to almost 80. It's a bit above 15. So yeah, it's much smaller. We just gained quite some space, huh? But that's not the only thing. The other problem is that we have static storage duration, which can increase the binary size. Yeah, so I'm always wondering how to ask this in the nicest way. So if there is anyone not familiar with the different storage durations, well, we'll just go through. So you have the automatic storage duration for non-static, non-extern, non-thread local variables. So you see some stuff that have automatic storage duration there, like the parameter for the function, the local variable, and even that member of the class that yeah is not non-static. Okay. Then you have static storage duration for static variables, hence the name, namespace level variables, and extern variables. They all have static storage duration. You have the dynamic one, which is for heap allocated variables and for exceptions thrown. And you have the thread local storage duration for thread local variables. We're not going into multi-threaded programming here today. So you have these 4 different kinds of storage durations, and yeah, it matters for your binary size which one you use. So the static one can increase the binary size. So we saw that, well, we had that array. It was on the global level. We didn't, well, it was not marked static, but it has static storage duration, and these global static variables can have big impact on binary size, because here the data might end, well, it might end up in different sections actually, but it might end up right there in the binary. That's why you rightly calculated that, well, the size must be at least 80K. For locals, it won't make a big, well, for local automatic storage durations, you won't get huge binaries, even if they are const, because in that sense, they won't end up in the binary. The data won't end up in the binary. It will be always calculated at runtime. But if you use constexpr, that can change things a little bit. So you can see some numbers here. Again, it's the same example that we used in the beginning. We just changed the storage duration for the container. So you have global. That's the original example. It was about 100K. If you make it to local, it will go down to 33K. But again, you see that the runtime goes up, because then that array will have to be created at runtime. It's not part of the binary. If you use local static const, it depends. It depends on the optimization level. So with O3 and OS, you get 60. Otherwise, it can be almost the same as before, and is the same with local constexpr as well. So again, this is the second factor that contributed to that big binary size that we saw for that tiny piece of code. Again, this is the original one, 78K for the data section, And when we have a local array, well, it shrinks again to 60. It's almost the same as we saw it when we replace the array with a vector. For local const array, it depends. It depends on how you compile with what optimization level. If I remember well, this is I didn't note it in the binary file. But it's right there. Yeah, it's 0. So with basically without any optimization, you get 78. But when you activate optimization, the compiler is smart enough to move, to basically get rid of the data section almost completely. So it's much smaller there. But that was only the second factor. So we saw the importance of what container you use. We saw the importance of storage duration when it comes to binary size, but the initial values also matter. They can matter. So let's take the original example and we'll change the values from 1 to 0. So remember that in that node struct, well, A and B were initialized to 1. Now we initialize them to 0. Do you expect the binary size to change? That's a very bad leading question. Yeah, it shrinks from 99K to 16K. That's a lot, huh? So the compiler now can optimize the initialization. And if we look into the assembly code, you will see that, well, originally we had this long one, 80,000 times. Luckily, I don't list all of them here. It would take quite some time to go all over. But otherwise, if you initialize everything to 0, then you have only one command instead, a zero fill command for 80,000 bytes. Instead of 80,000 instructions, you get only one, just because you use the default value for those types, ints. So what happens if we add another member? Well, zero fill will be still used. So it won't really impact the binary size, even if you add one more variable. Whereas if you use their 1 as initial values, well, if you care about binary size, that's not a good idea. So you see that it's still the same. No data, or well, very little. Well, actually 0 or 8. No, it's 0. Yeah, it's completely 0 there for the data section, data segment. Well, if you add something that needs runtime initialization, the binary will grow more, because you have to generate the code for that. For strings, it will also, well, it might depend on. Well, everything can depend actually on the different compilers that you use, but the trends are usually the same. But you see that even here we could use zero fill, but there are some more comments to be added. But we are still quite fine. But here data section reappears again, but only for those parts, only for the parts that need some runtime code to be generated as well. And we'll discuss also member ordering when it comes to objects. But first, we'll go to padding and alignment, what they are. So padding is the extra bytes between the different members, and alignment requirements, well, basically is for the memory addresses. it will tell you, okay, where certain variables have to be, what kind of addresses they have to have. So let's take an example. An integer is normally 4-byte large, and an int will then have to start at an address divisible by 4. For a double, which has the size of 8-byte, well, it has to be an address that is divisible by 8. So if we take this struct that has an unoptimal order, because we have first an integer, size of 4, double size of 8, integer 4. You add that up, and you see that, well, that's 16 bytes. Yet, when you have the assertion on its size, it's 24. And it's because of the padding that has to be introduced in order to meet the alignment requirements. Because, well, you cannot just have that double right after the 4-byte long integer, because consider that, well, that int is on address 0, then the double would be on address 4, and that is not divisible by 8. So extra 4 padding bytes have to be added so that the double starts on address 8. And then the second integer, I2, starts at address 16, but consider that you have these structs next to each other in the memory. Again, 4 padding bytes at the end will be added. So you end up with 24 bytes. Whereas, if you order them by decreasing order, decreasing in terms of its size, then you can shave off the 8 bytes, because the double will start at address 0. The first integer then will start at address 8. The second one is divisible by 4. The second one will start on address 12, again divisible by 4. And when it comes to the next instance of optimal order, well, it doesn't need any padding, so that the double can start on something that is divisible by 8. It can be right on address 16. So this matters. But this won't always reduce the binary size. And that's why I put these slides here right after the object initialization slides, because, well, it's very related, because the compiler can often optimize these things away. Well, it matters when members are not initialized to the default values. So if we go back here, and if we initialize this to, not, well, these are uninitialized here, or it depends how you create your, how you instantiate optimal order, if it will get some default zeros. But if you explicitly initialize them to 42, 42, whatever, then the compiler won't be able to optimize away. So then it matters if it's 16 or 24, the size of these objects. But if you use the default value, most probably you will just get a zero fill comment. But it's still a good practice to order your members in decreasing order, because this is a best practice anyway. It will help with cache friendliness and your memory footprint. And depending on what kind of storage duration you use, what kind of default values you use, what kind of containers you use, if you use them in a container, well, it might help with the binary size as well. Any questions or remarks? Feel free to add any remark as well. Yeah?
Perhaps it's obvious, but why is this requirement that a double has to be aligned on an 8-byte boundary?
Why do you Do you need that? It's how you access memory. It's basically, have you been to Björn Fowler's talk yesterday? Yeah, I think he was the one mentioning that you don't read individual objects from memory, but you always read one word. And objects in memory, you know, they try to organize them. Let's say that you have 3, 4 objects in one word, and you can read 3, 4 objects once together, and you know exactly what at each instance should be on what address. So you know that if okay, you know that if it's the size of, I'm getting lost there. Yeah.
Yeah, if you're doing ARM development and you load or store a double on an unaligned pointer, it will set for. And yeah, unless you have some of the extensions. So the hardware is optimized and not allowed widths. And if you tell the compiler, yes, I do want to do this, it's to generate a function machine code just to load in one run. You quite annoying.
Thanks. Okay, thank you.
Yeah, I saw in like a table earlier you had the like the runtime and compile time, and I saw the constant expression array had the longest runtime. Just wondering why that is when it should be if it's compile time allocated.
Const expression doesn't. Yeah, it's not always compile time. Yeah, it depends, and yeah, you also saw that. But that's my bad with the table. That for the size, I added 2 values, O0 and O3. But for the runtimes and the compile times, I only used 1 value, whereas they will differ as well. But good point. Yeah. Well, we still have 10 minutes of this first section, so we'll start covering the special functions in binary sizes, and we'll see how far we get. So we'll start with this piece of code. We have a class, and we have all the special member functions defaulted, and we have an array. So that's our initial code for this. And we'll have 6 different versions of almost the same class. Well, we'll have inline default special functions. We'll have inline empty special functions, or more or less empty, for the assignment stuff. And we'll follow the rule of 0 as well. And so that's 3, but we'll double it because we'll have 3 with virtual and 3 with non-virtual destructors. And we'll see how binary size follows, how they change. And again, I remind you that not everything that helps binary size is the best practice that you should follow in development. So here are the results. Well, default non-virtual and rule of 0 non-virtual, they have the same size. Interestingly, when you have empty implementations, the binary size is larger. And when you have virtual functions, well, it didn't really behave in similar way. The empty virtual was the smallest one, and the default and rule of 0 is bigger. Does it make sense? No, no, it doesn't make sense all the time. That's why I say, does it mean that you should have empty implementations instead of default? Well, probably no, it doesn't mean that. But it's at least interesting to see. On the other hand, for the non-virtual parts, yeah, what is a best practice is also best for your binary sizes. It's interesting to see, and there it's also useful to note that well, when you default member functions, the compiler might be able to declare them implicitly, no except. It might be able to perform some optimizations that it cannot do if you provide an implementation, even if it's empty, because the compiler won't care if it's empty or non-empty. It only cares that okay, did you provide it instead of me? Yeah, well, it's not a good idea in terms of your efforts, in terms of compiler efforts either. So but we really see that the virtual matters a lot. And I go back to what I mentioned earlier, that in one of the books, but well, we had a debate on that with one of my friends said, okay, you shouldn't really read it like that, that you should make everything virtual. That's not what he meant, but it was really easy to take it like that. So no, don't use virtual if it's virtual destructor if it's not needed. I mean, if you have any virtual member functions, of course you should, but if you don't plan to have any, don't just make your destructor virtual, because they will always mean an overhead. And it's interesting to see from these numbers that the default implementations can differ from the empty ones. But classes are rarely used as such. So let's go and see some more realistic examples. So, because here we had one main CPP and we had the class there, we declared the array there, but that's not really real life. Usually you have your classes in their own header files and implementation files. And let's see how things will change. So in main CPP, we only keep the main. And we'll move the definitions out of line, meaning that we move them from the header to the CPP file. And we'll compare virtual and non-virtual results separately, not in the same table anymore. So what happened? We have the default implementations for non-virtuals, header only, separated. The empty, header only, separated. And we see that here the default and empty implementations have the same size when they are separated into header and implementation. But when they are header only, well, it really depends on the optimization level. And the empty sometimes ended up to be a little bit smaller, just a tiny bit. Still not the best practice to use, but it's interesting to see. So if you take this data, well, what can we say about Newtonian physics? I want to make an analogy here. Well, it works sometimes, but if you go to some really small scale, you will need quantum physics. If you go to higher upper scales, you need relativity theory. So this explains, well, what happens on a small scale. Not tiny, not huge, small scale. But there, on a big scale, where usually you are in a corporation, it's not so good. It doesn't describe it well. So what should we do? Should we default or not to default? Well, whatever the numbers say there, I think that you should follow the rule of 0. That's core guideline, that's the best practice, that's the best you can do. Otherwise, follow the rule of 5 We'll see why, the rule of 5, by the way. And use default whenever possible, because at the end, the compiler is smarter than most of us. But where should we use the default? If you have a class that has a header file, and it has an implementation file where you put some business logic, where should you put the defaults? In the header or in the implementation file?
It depends.
Depends on what?
I was hoping that would be enough.
No, this is not an economics course here.
Does it depend on the research, like the empty instructions?
No, here just the default. Where we put equals default, where would you put? In the header on the implementation, and why?
There can be a constant size to what the compiler decides to use for the default. So you put it in a separate file, it happens once. You put it in a header file, it uses it in multiple places, but it can optimize it away, so you don't do this right.
That's a very interesting answer, and I think that we can continue from here after the break. We finish with this question here. Do you have? It depends, and we'll see. We'll see. Do you have any questions or remarks?
Yeah. One of the things that I'm wondering really is how much overhead is dynamic in practical applications, because that is something that my work, we have large shared libraries, and a lot of them are single use, they're used for one program. And say, I look at it and go, how much of these relocation tables and the relocation code adding to overhead have you looked at?
No, that's not something I looked at, but it's a very interesting question. So, I didn't mention in the beginning, but yeah, if I and no one else here can answer some questions, so maybe someone else could answer this question, I will try to cover it in a blog post during the next few months, and share it back to the Discord channel if you join there. But it's interesting, and it's interesting about reusability, because you often, okay, let's reuse this code, we distribute it to a shared library, and it won't be used anywhere else. That's quite common, right? Well, then thanks a lot. Enjoy the break, and I hope to see some of you, most of you, back. And we close the first session with a question. So if you have a class where you have all your special member functions declared and actually defined with default implementation, where should you put the default? That's the question. Should you put it in the header or in the implementation file, in the CPP file? And someone tried to answer it in the economist way, saying it depends. But and that's actually true, but we don't only stop there. So any other answer to this question? Where would you put the default? In the header or in the implementation file?
Header.
Why?
Because if you're putting it in the implementation file, then there would be an extra step of linking it, basically.
I see what you mean. Yeah, I wouldn't call it, yeah, it's not about linking it, but it's true that you have to call the function implementation then. You cannot inline the implementation of a special member function then. And yeah, so I asked this question once for a different reason, in fact. I asked this question on Twitter, and I pinged some people who I know. They know C++ much better than me. For example, I pinged Jason Turner. And he said that why on earth would you put it in the implementation file? Because if you'd do this, you put the def, well, what do? Okay, you declare your special member function in the header, but there is no implementation there. There is no default there. So basically, you sign out to the readers that and to the compiler that, well, there's something unusual, something unusual, something interesting that will happen there. And then you put default in the implementation file and say, well, I lied. In fact, yeah, it's the compiler cannot know at certain times that it will be default, and it cannot do certain types of optimization, might not be able to do that, and it won't be able to inline as well the implementation, and that's the key. That inlining is the key. At least my mouse, that works. Oh, come on. I'm not lucky with this one. Yeah?
So maybe when the default implementation generates a lot of code, then you might have only one copy of it if you put it in the implementation.
Exactly. Exactly. So actually, normally, putting the default, it makes sense in the header file for the, say, the obvious best practice-y reasons. It's readable for us, and for the compiler, it's also helpful. But there's one reason to do something else, and yeah, it's about limiting inlining. Because if you move it out of line, well, then the compiler cannot inline the body anymore of the defaulted function. And then the same piece of code won't be repeated over and over again. And this might matter in a big enough scale. Does it always matter? Well, probably no, but you can probably, test it and measure it if you really want to optimize for binary size. So something that we discussed during the break is that, for example, in every pull request, we generate some numbers. We measure how the binary size is affected by a pull request, by some changes on the different platforms. So if you raise a pull request in the Spotify client, Spotify C++ code base, then you will see that, okay, this change, maybe it doesn't affect the Windows binaries, maybe it doesn't affect the Android binaries, but it affects, I don't know, just saying a number, by 40 bytes, the iOS binaries. So if you want to do these kind of optimizations, yeah, you can try and you can measure. And I would really suggest the same in all code bases where this matters. So on a big enough project, these out-of-line defaults can actually shrink the executable. Now, if you do this, there are a couple of things to note. So I keep repeating this very same idea over the session. So optimizing for small size doesn't mean that you are following a best practice. You shouldn't really default out of line unless you have a very good reason to do so. And we also saw that sometimes even the empty implementations were smaller than the default ones. Well, you shouldn't do that. Still, it's better to let the compiler do its work and use the default implementation. No, you don't replace it with empty. But should we default in the CPP instead of the header? Well, maybe that's what you want. But then make sure you measure the effects. And you have to do something else as well. Because, yeah, where to default? By default, you would do it in the header. But if you do it in the CPP file, remember that this is counterintuitive. So what will happen? Because we said it's misleading for everyone, for the reader and for the compiler. So what will happen? There will be someone coming on your project and start moving the defaults to the header file, because they think that it's just a bad practice that they found in the project, until someone says in a pull request that, hey, we do this for a specific reason. But you know, maybe it won't be on the first pull request, not even on the second, because well, not everyone is aware of this. I've been there. I started to remove these from the implementation files, because I still remember that Twitter thread we had with Jason Turner that I mentioned. It's like, okay, you don't want to do this. They said, well, actually, here you want, because we want to limit the binary size like that. So if you do this, please document well and at a well visible place that you do this, because it's an optimization. It's not just a best practice, it's an optimization, in fact. And maybe people will not undo it then. So speaking about special member functions, keep in mind that if you have move operations that are not declared, they might hurt you. And I referred to this when I said that, well, if you cannot follow the rule of 0, you should follow the rule of 5. So let's have a look at the Hinnon table. Yeah?
Yeah, one more question about the previous, because you're moving on now. Is there a way to detect when this is beneficial? Is it especially large objects with a lot of large members inside, or what is the pattern that you have to look for when this might be beneficial?
Well, I would say it depends. Well, it depends how desperate you are. Because if you are looking for each byte, yeah, probably then it's what kind of, how many and how, let's say how many members you have and how difficult it is to initialize them. But otherwise, what I would look for is how frequently they are used, because you're limiting inlining. And if it's distributed through over, well, if it's used over several shared libraries, for example, or it's used in many different translation units, if it's used in bigger arrays, then probably you should focus on those. But again, what I just mentioned, I would say try to automate these measurements. If you care about binary sizes, try to do it in the CI. Try to measure them in the CI and just push it to the pull request the numbers, and you will see. If I'm unsure, usually I do that. I just raise a very small pull request, and I try to see how it affects the binary size. And then if you need more details, then you know, you can generate it for yourself and look it into with different tools we saw in the beginning of the previous section, like Bloaty from Google. That's then it's very useful to you.
So you look for small objects that are used a lot, or large objects?
Well, large objects that are used a lot.
Yeah.
Yeah. Yeah, I think so. Yeah. Yeah. Welcome. Thanks for the question. Yeah.
Yeah, I was just wondering, and it probably doesn't work, but what if you were to, like, I know in MSVC and GCC you can have like attributes to force non-inline when you declare function. What if you were to combine that with default in the header with that?
Yeah, you know, maybe you can try that, but then again, it's not that you said it's not a standard attribute, and it makes it a bit more difficult to compile everywhere and keep your code readable. So I think that's for example our main reason not to that's my main reason not even to try that there, because it's just easier to do this. But that might work as well, yeah. Any other remarks or questions? Okay, so let's get back to the hidden table. So we see that, well, in some cases, the move constructor and move assignment operator will not be declared if you don't follow the rule of 5. So for example, yeah, you see my cursor. You declare the copy constructor and I have the mouse. So, and then your move constructor, move assignment won't be declared. I'm not going through all the cases, but the point is that the undeclared move operations might hurt you without you knowing that they hurt you. Because, well, what happens if you have no move operations available? Well, you will just fall back automatically to copies. And, well, that might not be good for you in terms of runtime performance, but here we don't really care about runtime performance because we are discussing about binary sizes. And even for your binary, it's not necessarily good because, well, they'll just generate usually more assembly code. The copy operations than the moves, so you might end up with a bigger binary. Now, it doesn't, you know, this is not always, it doesn't always mean that you will gain a lot, but I told you that sometimes you do things for your binary that are not best practices, but this is a best practice anyway. It's good for runtime, it's good for binary as well. So just one other reason why to follow the rule of 5, not only runtime, but even binary size. Now let's move to virtuals. So what does the virtual keyword do? Well, it will enable you to redefine some member functions in the derived classes, or actually just to define them there, and differs the function binding to runtime. So it will be during runtime when it's decided which function implementation is executed. So there's this small example here. We have a car with some abstract member functions, accelerate, shift. I have accelerate twice, sorry for that. So then you have 3 different implementations of this interface. So how does it look like, really? Well, it depends. This is not how virtual function binding is implemented. I think it's not defined by the standard, but basically all implementations follow the same pattern. So for each class, there will be a virtual table, a vtable generated that's on a class level, and they contain pointers to each virtual functions. So you see that you have that you have 2 different objects there. So like city car, off-roader, SUV, and then on the right side you have the vtables, and each vtable has all these function pointers to different implementations, and for each object you have the virtual pointer, the v pointer. That's how it really looks like. Now, why is this important? This has to be generated and it has to be stored. So obviously it affects the binary size. The question is how and how much, and does it matter how many, for example, does it matter how many virtual methods you have in a class? And or hypothesis is that a v-table, generating a v-table, would increase the size of your binary significantly. Well, it depends what you mean by significant, but I'll get to that. But then additional virtual functions would only further increase the binary size only by a little. So that's what I mean by significant, that generating the v-table is much more significant than adding one more virtual function. So I decided to run some experiment. Class name is virtual experiment. We have the destructor, and we have 3 functions. Okay, normally it doesn't make sense to make these virtuals. It's not the point. Just to have something that we can measure and that fits one screen. So, I compiled it with 0 virtual and with 4 virtuals and with 3, 2, 1. And I wanted to see how the sizes change. So, if you look at the binary sizes, you see that when we have no virtual anywhere at all, it's just about 16 kilobytes. But as soon as we have at least the destructor virtual, we have about 281 kilobytes, and each additional virtual function adds only a tiny bit of size. So if you look at it, here it's 48 kilobytes. It might change depending, I think even depending on optimization level, but definitely depending on your compiler. But from here, we can see that, well, what matters more is adding the first virtual. And then the next ones, they just one extra line in the table. But generating the table takes probably a lot of time. I didn't really check for the time, but it definitely requires a lot of space, which brings us back to the thing I refer to. I refer to a book. Yeah, don't declare something virtual if you won't need it, because it's not. It doesn't only affect probably your runtime, but also the binary size. So if that's what you care about, well, then spare those virtuals. So here, what I changed is that I changed the initial values from 0 to 1. Because if we do that, we already saw in the previous session that we can avoid quite some optimization by the compiler, because then it won't be able to call just one 0 field comment to initialize a big chunk of space for you with zeros, but it will do one by one for each member, each instantiation. And even here, we see that when optimization cannot be done, just the addition of a virtual destructor means that you increase the size by almost 150K to 280Ks. That's a significant change for what? Well, for what it depends.
What are you measuring? The executable or the object file?
The executable, the final binary, the final binary. Yeah, yeah. Because in our example, that's what matters for us. That's what matters. What you download at the end and you install on your phone. Yeah, that executable is matter. So the single virtual destructor has a big price, but you'll have to pay that price in any case, even if it's good for a compiler for optimizing that we saw with default 0 initial values. And even if it's not good for optimization, there's a high price to pay. But once you know that you need, for whatever reason, you decided to go with a polymorphic structure, you need at least one virtual function, or, well, the destructor, the rest doesn't really have a big price. So you might end up in a, no, I don't think that you'll really end up in a situation where these 40-something bytes will matter. If those matter, you will find a way to avoid even having the first virtual destructor. If you already have a virtual function, probably you don't really care about the rest. You're free to add functions as you need.
Is that a per class? That initial overhead for the first virtual function, is that per class, or is that code that gets linked in to support it across?
That's per class, yeah.
That's absurd.
Is it? Well, look, everything has a price. You get some features, you have to pay the price. And again, you have to put this into context, because on the one hand, you say that, wow, okay, I don't know, we doubled the binary size. But that's one way to see it. The other way to see it is like, okay, we added 100 kilobyte extra, which is not necessarily that bad. But I know that a few months ago, I just went through the code base, and somehow I managed to list all the classes that only had a virtual destructor, but they didn't have any virtual functions. And I just removed those virtual destructors. And in the end, what did we gain? I think I don't remember exactly. It was a few hundred kilobytes, I think, but it was not a lot. We didn't have a lot of such classes, luckily. But at least we gained something for losing nothing.
Yeah, I'm just wondering, does it scale at all with the amount of implementations? Does it matter how many implementations, or is the V table roughly the same size, no matter how many derived classes there are? Does that make sense?
I think it matters how many derived classes you have. Yeah.
But I don't mean in terms of the size of derived classes, but the size of the V table itself. I don't know.
Yeah, size of the V table.
Okay.
Yeah. Okay, let's move to templates and binary size. So it's important. Well, maybe I'll say something obvious, but it's very important to understand when you use templates, because if you understand when you use templates, you can start thinking about what kind of templates you use. And remember that even like years ago, we had these discussions like, okay, we are afraid of templates. In some previous company, some otherwise thinkers, a good engineer told me, don't use templates. They are dangerous, they are difficult to understand, and no, just don't do it. Like, well, I think they would help. No, don't do it. Well, fair enough. But probably there are less and less people like that with modern C++, where templates are more, let's say, accessible and easy to use. But even if you say that, you don't want to use templates, you probably use templates. Use templates even when you don't think you use. Probably you know that you use templates, but you don't even think about it through the standard library. Almost sure, even if you just use a standard string, well, it's just an alias for, what is it? Like basic string car, I think. But with modern C++, auto can also deceive less experienced people, and they might not realize that, okay, even without the template keyword, you can write templates. Well, that's probably important to keep in mind, especially if you care about binary size. So the first and probably most important advice that I can give you, and it's relatively easy to implement, is to use minimal templates if you write templates, because each template expansion will copy some code, and so the longer the code you have in the template, in the body of a function or class, for example, well, the more will be copied, unless the compiler is smart enough with some good settings to optimize some parts away. But again, you don't really want to rely on the compiler to make your code smaller if you can easily do it yourself. So keep your template small, even if it's a function or class template, and extract the rest. So what do I mean by this? Let's say that you have a long function template, and there is some part where you use your templated type in it, but then you don't use it. And for some reason, you just wrote your function like that. Well, in that case, extract that part that doesn't depend on the template part. So you'll have an extracted part, and you will just call that. And with that, when the template expansion happens, well, this code here will not be copied over and over again. Just the function call to it. So with that, you can gain quite some in a big enough code base. So obviously here, I cannot really bring you numbers because it real world numbers, because it really depends on what you have, and it would be just too difficult probably to identify those pull requests. You can also do this for classes. You can extract even like a base class from classes. I'll definitely share the slides right after the session, so you can extract the part that is not that doesn't depend on the template parameters to a base class, and use it in your original class template, and then you can avoid the copying of some code.
But this is still inline. If you put it in a header. So where's the difference?
Well, it has to fit the slide. Yeah, but you're right to point that out.
Yeah, but if you don't put the information into the header, then it makes.
Yeah. It's just a bit more difficult to show on a slide, but that's a very important point. Thanks for making it. Yeah. So who has used extern templates? Okay, 3, 4 out of 5 out of, I don't know, that's maybe like 20%. Okay, that's actually more than I expected, I think. So what do extern templates do? So extern otherwise indicates that the definition should be found by the linker, right? That's what it tells you. So let's say you have this code. You have a template class wrapper, and then you put their extern template class wrapper int. So this means that in this translation unit, no object code will be generated for the wrapper int expansion. Am I right? So with extern templates, you can limit the number of times that code will be generated for one specialization, which is good for compile time as well. I think there was a video dedicated on C++ Weekly to extern templates, and there Jason explicitly talked about the massive gains he got in terms of compile time. But it can be also useful for your binary size because less code has to be generated. So how to use extern templates? I can mention two different options. One is putting this extern template class wrapper int in every translation unit where you instantiate wrapper int. But, well, it might be straightforward, but it's a bit repetitive. And let's face it, it's easy to forget to do that. Another way that I found, and those who use extern templates, you can mention your experience, so that if you have the wrapper age where you have your template definition, there you can put extern template wrapper int in that header, and as such, anyone who includes this wrapper.age will have the extern template as well, because, well, it's just include is just what is the textual copy. And in the wrapper CPP, you can put the explicit declaration of this template class wrapper int. So the code will be generated only there. Necessary code, and then the linker will find it. So that's the example for that. You have the wrapper.age, we have the extern template class wrapper int right below, and then we go to wrapper CPP, and that's where you have your explicit template instantiation, and well, then you will just include wrapper A wherever you want to use the wrapper, and well, the linker will do the rest. Are they worth it? Are they worth using? Well, if everything happens, I think I didn't put here all the numbers, but if you use it only within one library, I found that well, it was quite limited how much you can gain, especially if, for example, that wrapper.cpp didn't exist before. If you created only for this, it was very limited. But if you use that externalized template across libraries, then you can gain a lot, especially if used widely. It's worth noting that with this, you also lose kind of the inlining. You might lose the inlining, which we said that often we want to avoid in any case, but sometimes it's still useful. But if you use link time optimization specifically, then you will get it back. Yeah, I didn't put here the numbers, but I mentioned in the first session that there is a small ebook available, and you will get the links to download it for free. At the end, I'll share it on Discord, and there you have more numbers that didn't really fit the slides. So one more thing is to avoid bloaty class templates. What are bloaty class templates? Well, yeah, it depends, but even you will even find some even in the standard library. But okay, usually the more functionalities a template provides you, the bigger it will be. That makes kind of sense, right? Well, if binary size is critical for you, think twice before you introduce anything more. And as I just mentioned, standard and boost types are no exception to this. They can be, well, they can be quite heavy. And with that, we jump to how to pass functions to functions. So you have plenty of options if you want to pass callables. You can use stud function, speaking about bloated templates. Well, it's relatively readable, right? You use stud function, you use the return type and the parameter types. Well, it's kind of okay. You can use bare templates, but well, it's not really the same, right? Because you could pass there anything. So you can use not so bare templates. You can use to the invocable, for example, or here, well, we use the requires clause as well to limit what kind of callable would be accepted by this foo, and you can achieve pretty much the same. Not pretty much the same implementation, but at least pretty much the same constraints that you have with stud function. Or you can use function pointers as well, which yeah, it's not very readable. Probably that's the worst part with it. But you know, you can make it better with some aliasing. It's much better, I think, like that. Well, you have different options at least, and the different options, well, have different advantages. And we said that function pointers, they have not so readable syntax. Depends how you define readable or what you are used to. But, well, personally, I don't find them very readable. Stud function works very well out of the box and with any kind of lambdas, meaning that you can use, with stud function, you can use lambdas with captures. And you cannot pass lambdas with captures to function pointers. And then you have templates, and they are quite specializable with concepts. Well, we already said that templates can significantly bloat the binary, but stud function is also a template. And it, as I said, it offers a lot of functionalities, and therefore it's quite bloated. So let's run some experiments. We have this perform operation there, and here we take a very nice and readable function pointer, and well, we just perform some operations, and we measure the size, and we can modify perform operation to take instead of function pointer, it will take a template, it will take a stud function. And everywhere I used optimization. So you see that the binary size varies quite a lot between template, function point, and function. So stud function, with stud function, you get an extra 5K compared to using templates or function pointers. And for templates and function pointers, you basically have no difference, or almost no difference. Probably that kind of difference doesn't matter, but stud function matters. We gained quite a lot by just replacing stud function in our code base, actually with an own implementation of stud function, which probably doesn't do so much, but it's more than enough for us. So with that, I'll quickly jump to the observer pattern and binary sizes, because this will connect to the usage of stud function. You'll see why. So a few words on this pattern. Yeah, I don't know why I did the typo there. I put here the decorator pattern, but it's clearly the observer, which is a behavioral design pattern. And well, here an object can notify other object about changes in their state. I'm not going to walk you through the whole code example, but these examples, let's say they are courtesy of Klaus Egelberger. He doesn't know about this slide, but when I wrote a blog post about this, I asked him, can I use some examples from your book? And he said, yeah, it's completely fine. So I basically took two implementations of the observer pattern from his book, one classical based on runtime polymorphism, and another one that is more based on various semantics. So you have this classical interface where the address observer inherits from an observer template, and you see that we have there an update function, and well, we create a person, we attach some observers, we change the address, and then, well, we accept some notifications to happen. And there is the modern interface, which is kind of similar, but yet it's kind of different. You still have this observer template, but when you instantiate, for example, this person observer, you pass in an onUpdate function, what should happen on update. You don't create a derived class for that, but well, you pass it in to the constructor. Two different approaches, one classical, one modern. And well, how you implement the modern can vary based on how you pass in your functions. And here there is probably a surprising result. So if we focus on what's in bold, you will see that the modern observer is significantly bigger than the classical one. It's a bit more than 10%, even though compile time was a bit smaller. And what's interesting here is that I implemented then the modern observer with different ways of passing the pointers, passing the functions. So the previous numbers were with stud function, and you see that classical observer, it has a big advantage. Well, it has some advantage in terms of binary size, but if you use function pointers, or if you use one function pointers and the lambda, you see that that relationship, which one is bigger or smaller, it changes completely. So what do I want to say with this? Well, if you want to choose, for example, an implementation for the observer pattern, well, it matters, of course, which way you want to go, the classical way or the modern way. But it's not enough to just choose the right design approach, because the details will matter a lot. So when you go into details of an implementation, it matters how you implement that design a lot. So stud function is relatively, well, it's explicitly bloaty one. If you have to pass functions around a lot, then avoid stud function. So I would say I would go with templates or function pointers, because they will be faster and cheaper, and probably they are not more readable. That's a price to pay. I find stud function relatively readable, and revisit this decision in the future, because probably you are somewhere, hopefully, well, if you are lucky, on C++20, but with 23, 26, you'll get move-only function, you will get function reference, and it might change these numbers. So if you depend on these kind of things and binary matters to you, then revisit it I would say every few years. Check what new standards bring to us. Let's talk a little bit about constexp functions. So they might be executed at compile time. It's good that they guarantee that you have no undefined behavior because it cannot exist in compile time. That's the good thing. And they also guarantee implicit inlining. Okay. And do we like inlining? Not necessarily. Still, if we experiment with 3 versions of a piece of code that we'll see, we'll see some interesting numbers. So once we'll have the code used only in one translation unit, in the second one with several translation units, and then in a third example across different libraries. And this is the example. We have a function there that just does some division, and we use it. We can use it with constexp, with inline, and with nothing at all. And interestingly, there is no big difference for a single use. Well, at least the way we used it here. But usually you don't use functions like that. So it's worth moving on to different experiments. Well, we see that there's no big changes. And if you check the intermediary assembler file, what you will find that the const exp was never bigger than the other versions. With multi-translation unit use, there's still no big difference. Everything is around 39 kilobytes, whether you use const exp or non-const exp, and even here the optimization didn't really matter. How I did the test? Well, I moved that fun into let's say into utility header, and we had 3 classes using it, and yeah, you see it's small. Usually you wouldn't really care about this kind of difference, but when it's distributed to a shared library, well, then things started to change. So we have a SO file, and the size of the SO file didn't change whether the code in it, the function, it is declared const exp or not. That didn't change. But their users, the other libraries that are using this util library, their size significantly changed. And if you combine the sizes of the different binaries, the libutil shared library and the libraries that are using it, you see that when that function was declared as const exp, you ended up with something much smaller, because well, things could be done at compile time, and the code didn't have to be copied over and over again. And even changing the funds implementation, it didn't really matter. So I tried it with a bit bigger function instead of just one division. I made something bigger, but it didn't change this relationship. So what we've seen is that const extra never really hurts in terms of binary. Well, it never hurts at all in terms of binary if you use any kind of optimization, and even if you don't use it, only had very limited effects. But it can bring significant benefits. So one more reason to try to make your functions const exp if you can. And with that, we close this section, and we will review some compiler and linker settings before we finish with RTTI and exceptions. So again, something to mention about compiler and linker settings. We had great fun in our teams when we worked with different ways of coding. We learned a lot. We enjoyed it, and we could brag that we removed, I don't know, 8 kilobyte with this nice change. When it comes to compiler and linker settings, you change one thing and you can gain megabytes depending on how big your binaries are. So yeah, it's important to play around with them. So we're going to see a couple of one. We cannot ignore the simplest one, OS. Then we'll look that link time optimization can bring you serious benefits in terms of binary size. Then we'll discuss a pair of options, data sections, function sections, and --gc sections, which we have to use together. We'll discuss why. We have another linker setting, ICF. We can strip symbols, US needed. There's a bit of a strange one, the inline threshold, which will make you experiment, but we cannot really say anything exact about it. And we'll discuss about the stack protector, which will not make your binaries smaller, but it can make your binaries significantly bigger. It's important to note that. So the simplest one is OS. O stands for optimization. It's one of the optimization levels. So you have O0 to O3 for optimizing for speed. And then you have OS or OZ, depending on the implementation, for optimizing for space. Optimizing for space is based on O2. So if you optimize for space, it doesn't mean that you give up runtime optimization, but it means that it will contain everything from, I think it contains everything from O2 and some others that don't make your binaries bigger. But there are some stuff that would make your binaries bigger. So for example, loop unrolling is something that would make your binary bigger, and it's not part of OS. So just for those who don't know, like let's say you have a simple loop, and it would call the same function like 5 times. If you use O3 or if you optimize with loop unrolling, it would mean that it would replace, compiler would replace your loop with 5 times the same code, because, well, that would probably be just easier and faster for it, but it's not good for binary size. So with OS, that's not gonna happen. That's the most basic thing to try if you want to decrease your binary size. If you already care about binary size, you probably already did that. You can also do link time optimization. I personally don't really like that name. I found interprocedural optimization a bit more descriptive. It's performed mostly by the linker, and it will go beyond individual object files. I say mostly by the linker. Why did I say mostly by the linker? Because it requires an extra step in the compilation process. So this is not something cheap, because you need some intermediary bit code created by the compiler, and then the linker will be able to extract some dependency optimization and perform some optimization and discard stuff, and overall make your binary much smaller. I remember something like 6% maybe that some teams could gain by turning LTO on, and if you have the time in the CI to perform these extra steps, then it's worth trying it. And it's worth trying it with different available options that will depend on your compiler and or linker, what is available to you. You have to check your documentation. But with the default LTO, FLTO is the default configuration. You can use thin for a bit faster but less aggressive optimization. You have FLTO full for maximum optimization. It will take quite some time, but well, you might want to try it. So FLTO full is sometimes also called whole program. Well, not sometimes, it depends on which compiler, which linker you use. In that case, every translation unit will be treated as a single unit during the optimization, and well, it really slows things down. And as it incurs aggressive inlining, maybe it will even lead to a bigger binary. So it's the same as with any kind of optimization. Don't do optimizations blindly. Measure the effects, and only go with a certain kind of setting if you think that it brings you what you expect. So it's an interesting one: data sections, function sections, and WLGC sections. So these two fdata sections and ffunction sections will place each global data and function into its own section. And this point, your binary is growing. It will be much larger. So you don't want to use these options on their own, but you want to combine these options with WLGC sections. And GC sections, GC stands for, I think it stands for, actually I didn't verify that, I think it's for garbage collection. It removes the garbage, it removes the unused sections, and maybe I'm completely wrong with the GC part, but it helps me remember. And at that point, you might end up with something much smaller. So when we speak about unused sections and unused code, it doesn't mean that unused sections are not the same as unused code. So here's what happens. Let's say you link a shared library, and the linker will include the entire text section. So it might include code from a library that you don't use, but well, others still do. So in that sense, it's not unused code. Well, it's library. You can't really know, but well, I think that's an important note, because otherwise you might think, well, okay, if it's unused, why don't we remove it completely? Well, it's unused in that context only. Yeah. Again, don't forget to measure and test, because each of these steps, each of these extra settings will not only add extra time to your compilation linking process, but it also gives extra complexity for your setup. And someone has to maintain that setup, someone has to read that setup, has to figure out what is there because of why. And well, if something doesn't bring you anything, just or something really insignificant, then just throw it away and maybe mention in a comment that you tried it, but it didn't work out well. So that's why it's not there. You can save some time for the others in the future. There is ICF. So I think I didn't mention that when something is preceded by -wl, comma, it means that it's a setting for the linker, and well, the compiler will just transmit it. Otherwise, if you call the linker in a separate command, then you don't need the -wl. So I would say that ICF, which stands for identical code folding, is, to me, it's kind of the don't repeat yourself principle applied on a linker level. And this has two settings, all and safe. So some Google experiments reported that just by using this setting, they could gain like 6% on certain binaries, which is not bad. By default, I would go with ICF all, but it might be unsafe. Well, hence you have the safe option. But when can it be unsafe? When can it be unsafe to remove identical code from your binaries? Any idea? Yeah?
If you compare function pointers,
Yeah?
that will go wrong, right?
That can go wrong. Yeah. So we generate code for identical functions, and for example, use functions are keys. So that's might be even possible. Yeah. That will be a problem, and you won't notice it, or well, you won't notice it until it's too late. So if you do such kind of things, then you just go with the ICF equals safe version. It will probably still bring you quite some benefits. So I'm thinking which one we use. I think we use all, and it's not a problem for us, for example. Well, there are some more to do. The -s, or in its long version, the strip all, which removes symbols, debug information, and actually information that is not essential for execution. Not essential for your release build, for example. In production environments, embedded systems, I think this can be really useful to use, but it makes debugging much more challenging. So yeah, I know, like, it really depends when you can do this. I mentioned why smaller binary size is important for us in Spotify. So for us, it's not a problem. It's if the debug binaries are huge, because users will not depend on that. But well, in certain like embedded environment, I know that could be problematic to have big debug builds. Well, again, I keep this repeating: measure before you commit to something. There is also the as needed option. By default, all specified libraries that you pass to the linker will be linked, but if you use as needed, well, it will exclude the unnecessary library dependencies. Well, if you need it, it probably also means that somewhere in your setup, you're a bit sloppy about updating things, removing dependencies that you don't need anymore. But well, this will do it for you. Link time optimization might affect this. So again, if things might change if you use many of these options combined. So it's worth revisiting and test them. There is this interesting one. Yeah.
So maybe the previous option is a nice way to detect if you actually have referencing things that you shouldn't be.
Yeah. Well, yeah, actually you can use it like that as well. You compile and link two ways. and you say, okay, if there is a difference,
If you have many benefits from this, something is wrong.
yeah, then something is wrong. You can use it like that. Exactly. That's a very good point. And then you can look into what is wrong. Then we have this inline threshold, or it's on LLVM, GCC, it's called inline limit. Look, the default number is 144. I don't know why I couldn't find it, but this affects inlining. It's to me this is a bit of exotic, but you can play with it and you can try to measure. I I played it with on our shared library in Spotify, and well, I just gave some nonsense numbers to it, and it increased by crazy megabytes the binary size if I gave too big number, but even if I gave a too small number to it. So I would say that's something that is worth playing with, but I found it difficult to get it right. I wanted to mention stack protector. So what's stack protector? It's something that will make your binary bigger, but it brings you some security features. So it helps you to prevent some buffer overflow attacks, and you might have to use it, but if you use it, you have different settings for that, and it will change the gain you have in terms of binary size. So what does it do? It inserts some random values on the stack before the return address, and that's how it limits some attacks. And it has different settings. So stack protector is the default. You can use it with the option strong. Then stack protection will be applied on more functions, so your binary will be larger than it would be otherwise. Stack protector all will be applied on all the functions. Obviously, that will make your binary even larger. But you can use it with GCC, with stack protector explicit, and you can add attributes to certain functions that where you want to apply stack protection. Well, that gives you quite a good control over the size gain that you will get. But I think it was you who mentioned earlier different attributes. Again, it's this I think is for only GCC. So if you want to work across different compilers, then you will end up with some less readable code at the end. And with that, well, we still have about 90 minutes to wrap up and to discuss ways of coding and compiler settings to remove binary size. So we'll talk about RTTI and exceptions here. We'll start with RTTI, binary size and RTTI. What is RTTI? Is there anyone who is not familiar with RTTI? It's always the wrong question to ask, but thanks for showing your hand. So it's a runtime type information, which is available for every polymorphic class where you have, for example, where you have virtual functions. It helps determining the dynamic type of an object, and you can query it in runtime and make some decisions based on that, or even to print some information. And it's a language feature that is turned on by default. If you don't do anything, RTTI will be generated. You can turn it off with -f no RTTI on GCC and Clang, and you have this gr- option on MSVC. So what does it give us? It gives us the type ID function, and what it returns, the std type info. You might use it to compare the types of two objects. You might want to to print it while you are debugging, and you don't use a debugger. You just want to, just to add some logging during your investigation. I think you can easily live without that. Most projects can live without that, but it also gives us dynamic cast, which along the inheritance tree, well, it will give you ways to safely convert pointers and references in different ways. And if you use it, you will often see it along with a huge bunch of if statements in your code if it's used incorrectly. And my personal opinion is that in most cases it's used incorrectly. So you might see something like this. Now, obviously, this is a bit exaggerated, but well, I think many of you will, just recognize the pattern. You try to dynamic cast to a derived object, and you check, well, okay, if that pointer is not null, then you do something. Otherwise, you try to do something similar and similar and similar. And this will not make your code better. It will not make your code more readable. So, is this good? Is it a smell? I know that there are some disagreements between certain people on this. I think this is more a smell than something good. I think without dynamic casts, so without runtime type information, you can get a cleaner interface where you rely more on nice and tidy interface for polymorphic objects instead of trying to manually cast things. So in that case, you let the runtime to do the dispatch instead of coding it manually. But what do we gain with that? That's the question. Well, I think we gain clarity. We get better code, we get cleaner code. And we gain subspace in terms of lines of code written, for sure. Does it necessarily mean that we'll have a smaller binary? Well, probably, yeah. Probably it does. Well, I tried some smaller examples, and you see that, well, if we check, okay, with dynamic cast 03, my example, which is based on the code that I used, was 37.3K. Without the dynamic cast, but the RTTI still on, it was 37.2. And then if I turn RTTI off, I could spare some more. Is this a lot? No, it's not a lot. But it also made your code cleaner, and it also made your compilation a bit faster. So I think there are good reasons to do that. There are good reasons to disallow in many cases. I'm not saying in all the cases, but in many cases, RTTI, because I think that the dynamic cast is usually misused, and there are much better options. I discussed with someone from a different company, and he shared a couple of examples where he thinks that dynamic casts are necessary. But for example, he even agreed that usually it's misused. But okay, there are some cases when they are necessary. But if they are not, well, then maybe you can try turn it off. It's easy to do it in a project that you write from scratch. It's not so easy if you are working on something big where dynamic cast is already there. I know it was a big effort. I cannot tell you how much time it took in our code base or the exact number it brought us, because it was before I joined and I didn't find docs on that. But in general, people were very happy with the effects of it. So why not using it? So let's talk a few minutes. We have 12 minutes left about exceptions and the binary size. So, as you see, not every CPU operation is made the same. There are some stuff that is really inexpensive, really cheap, especially if you read something from if something happens right in the CPU, or you read something from the closest caches. But when it goes to exceptions, it's somewhere down there. Exceptions are quite costly, right? But does it matter? Because many people say that, well, exceptions are zero cost. Well, they are zero cost when they are not thrown, right? But even that is not exactly true. Yeah, runtime costs are zero if an exception is unthrown, and often you can say that, well, an exception is costly when it's thrown in terms of runtime performance, but it doesn't really matter because probably you are already on an unhappy path, and there, well, if they are used correctly, and there probably the runtime performance is not so important anymore. But even if you consider that, we only talk about runtime costs. The compilation time must be slower because, well, you have more code to compile. You have to generate what should happen, should happen at runtime if an exception is thrown. That has to be generated, and it has to be generated. It takes time, but it has to be stored as well. So the binary size will also grow with the exception tables and unwind information. So what if we could turn off exceptions? Then exceptions cannot be thrown. And if they are still thrown because you use a library that throws an exception, std terminate will be called immediately. Your program will end. Well, is that a problem? Depends. It depends. So I said, okay, let's try some very small example. We had that class quite some time ago where you had all the special member functions defaulted. What happens if you compile with exceptions being turned off? So you have to pass -f no -exception. And, well, nothing. Exactly nothing happens because they were already no except. No exception could be thrown. The compiler already knows, so nothing had to be generated. You gain nothing. Well, it's not really the numbers we were looking for. It doesn't prove our point, right? What about a more complex case? The observer pattern that we took from Klaus. Well, there, without exceptions, we gained something. Lot? No, we didn't gain a lot, but still, well, it's a small difference. So if you compile with exceptions and you check your assembly code, you will find some exceptions tables, comments related what should be done. Otherwise, well, it won't be generated if you turn exceptions off. So that's from where you get the gain. If you cannot turn off exceptions because you've been coding for a long time and it would be just way too costly to remove them now that you realize that you want to gain something, because it's still something that you can gain, you can use no except. And you can specify whether a function can throw an exception or not. And with no except, you can show that, well, this should not throw anything, which means to the compiler that it shouldn't generate any information related exceptions being thrown. Otherwise, if somehow still an exception will escape that function, to terminate will be called. So that's something you can use. But look, I put no except everywhere with the observer pattern, and I ended up with a bigger binary. How is that possible?
Extra string terminate calls if you actually throw inside there.
It's a good guess, but no, it was a bug. So there were exception tables everywhere, and it turns out that it was just a bug. So I tried this with Apple Clang, and after some googling, I found an RFC on llvm.org, and they complained about this. So what's my message with this? Measure, because you know what should happen, but maybe it's not gonna happen because, well, compilers are software too. They can be buggy. Well, they are buggy. It's normal. So don't just think that I do something that makes sense and it will be fine. Measure it. So with reaching to the end, what are the main pieces of advice after this time we spent together? Well, it's very fun how you write code, and it will bring you a lot of joy if you can refactor a bit and remove a few kilobytes here and there. But first, check your compiler and linker settings, because they can bring you much more, and depending on your context, probably they will bring already enough gains, or actually not gains, but the opposite. You can shave off already enough from your binary with just using the right settings. Try to prevent inlining if size still matters to you. That's what we saw with, for example, with defaulting in the implementation files. But it's not a general best practice. You have to try and see. Whether you want to use exceptions, try to think about it in the beginning and think about it twice. You can gain quite some space. Here it was small, but some other people who could actually compile without bigger projects without exceptions, they reported more significant gains. For us, it's not possible. We cannot remove exceptions in a reasonable way. We might need that, but try to make no except whatever you can, but measure, because depending on your compiler, you might not get what you want. But with others, for example, we gained quite some just by using no except. And don't use virtuals in vain, because they will make they will make your code probably slower. They will make it definitely bigger. And if you have better options, if you don't need them, well, just don't use them. And I would seriously consider turning RTTI off, because I think that in most cases, it's the RTTI is not needed, and it will only give a tool into your hands that will help you making your code worse. And if you can live without it, then good. You'll even get a smaller binary. So again, we think about templates and how you pass functions around. Well, think twice, because if you use the stud function template, it will probably cost you a lot, and it's quite easy to get rid of it, and you can get some significant benefits by doing so. So what to do with all these information? Well, at least you should be aware what and how will impact your binary size. You might not care, but it's good if you at least understand this is just a way of optimization. You can optimize for many things: compile time, performance, runtime performance, binary size, whatever. This is just one more thing to optimize for. And try to avoid the traps that we saw. And if you go back to your teams and you found some interesting parts that you could use, well, share knowledge. That's the best you can do in any team, in fact. And thanks a lot for joining these 2 sessions. It's been a pleasure.